Hello, everyone. Today's lecture topic is fundamental to understanding how modern DBMSs ensure data correctness and integrity. We will talk about transactions, a mechanism that allows complex operations to be executed as a single unit. And we will look at how systems manage data access when hundreds of users are working with it simultaneously. Today, we will cover 5 key blocks. We'll start with the definition of a transaction as a logical unit of work. Then, we'll delve into the ACID acronym, the 4 components of database reliability. After the theoretical part, we'll move on to practice. Which SQL commands are used to manage transactions? Then we'll discuss what happens when many users modify data simultaneously and what problems we might encounter. Finally, we'll find out how isolation levels help solve these problems. Let's start with the definition. In modern DBMSs, a transaction is a fundamental logical unit of work. It is a sequence of data manipulation, DML, operations that is absolutely indivisible for the system. The key principle here is all or nothing. What does this mean in practice? A transaction cannot stop halfway. Consider the classic example of a bank transfer. Technically, it consists of 2 operations, withdrawing funds from the sender's account and depositing them into the recipient's account. If the system fails, for example, a power outage, after the first action before the second is completed, without transactions, we would have a situation where the money simply disappeared. The transaction mechanism obliges the system in such a case to automatically cancel all changes and return the database to the state that preceded the start of the operation. This very mechanism is the main guarantor of data integrity, ensuring that the database is always in a correct state, even if errors occur. The reliability of transactions in databases is assessed by their compliance with the ACID standard. This is an acronym describing 4 key requirements. The first is Atomicity. It guarantees that all operations within a transaction are a single unit. If at least one command fails, the entire transaction is rolled back. No half-completed states. The second is Consistency. This property ensures that the transaction does not violate the business rules of the database. After the transaction is completed, all data must comply with integrity constraints, e.g. data types, foreign keys, cascading rules, and triggers. If a transaction attempts to violate these rules, it is rolled back. The third is Isolation. In real systems, many transactions run concurrently. Isolation ensures that the intermediate results of one transaction do not affect another. Perfect isolation creates the illusion that transactions are executed strictly sequentially, one after another. The fourth is Durability. It guarantees that once you receive a message about the successful completion of a transaction, commit, the data is saved forever. Even if a system crash or power failure occurs a moment later, the information will not be lost thanks to logging mechanisms. In the SQL language, a separate group of commands, Transaction Control Language, TCL, is used to manage the lifecycle of transactions. The start of work is marked by the Start Transaction command, or the Begin command. From this moment, automatic commit, auto-commit, is disabled, and all actions become part of a single session. The commit command is used for successful completion. This command writes the changes to disk and makes them available to other users. If an error occurs or there is a need to cancel the actions, the ROLLBACK command is used. It returns the database to the state it was in before the Start Transaction command was executed. Let's consider the classic example of a bank transfer, where it's crucial that both operations are executed together. We start with the Start Transaction command. Next, we execute 2 separate update queries, debiting funds from one account and crediting them to another. At this stage, the changes are not yet permanent. Only after both steps have been successfully completed do we execute the commit command, finalizing the transfer. If a failure occurs at any stage, for example, insufficient funds in the account or a lost connection, the ROLLBACK command logic will be triggered, and the money will be returned to its original state, as if the operation never happened. When we move from the theory of a single user to the real world, where hundreds of people work with the database, so-called race conditions occur. The most well-known problem here is the dirty read. Imagine a situation. Transaction B changes some data, for example, the price of a product, but has not yet pressed the save button, i.e., has not performed a commit command. At this very moment, Transaction A comes along and reads this new price. Everything would be fine if Transaction B completed successfully. But if Transaction B suddenly cancels its changes with a rollback command, a collision occurs. Transaction A has already read a price that never actually existed in the committed state of the database. It continues to process this erroneous information, which can lead to serious financial or logical errors in the business logic. Let's look at the mechanics of the problem using an SQL code example. First, Transaction B updates the products table, setting the price of the product with ID 1 to 200. Note that the commit command has not yet been issued. These changes are hanging in the air. During this interval, Transaction A intervenes and executes a select query. It sees this uncommitted price of 200 and uses it for its calculations, for example, issuing an invoice to a client. Then, for some reason, an error or a user decision, Transaction B performs a rollback command. In the database, the price instantly reverts to its old value. But for Transaction A, it's too late. It has already picked up the dirty data. The system is working with a price of 200, which de facto does not exist, constituting a violation of data integrity. The next typical concurrency problem is the non-repeatable read. The name speaks for itself. You cannot repeat a read and get the same result. The situation is as follows. Your transaction, let's call it A, reads a specific row from the database. While you are processing this data, another transaction, B, intervenes, modifies that same row, and, importantly, successfully commits the changes with the commit command. When your transaction A accesses this row a second time, for example, for verification, it sees completely different data. This is different from a dirty read because we are reading committed data. The problem is that the data changed right under our feet while our logic was executing, which violates the integrity of the system's state perception within a single transaction. Let's look at the code to understand the problem more deeply. In the first step, Transaction A checks the balance of account number 1 and gets the value 1,000. At this moment, another process, Transaction B, updates this balance to 500 and commits the changes. Since the commit command occurred, these changes are legitimate and visible to everyone. But Transaction A is still running. When it makes a repeat query to the same account in Step 2, it unexpectedly gets 500 instead of 1,000. If Transaction A's algorithm relied on the balance of 1,000 being constant until the end of the operation, for example, for calculating interest, then such a change will lead to a logical error. The third classic problem is the phantom read. It is often confused with the previous one, so it's important to understand the difference. The situation is as follows. Transaction A executes a query to select a range of data. For example, show all users with a balance greater than 1,000 UAH. Let's say it finds 5 such records. Meanwhile, a concurrent transaction B inserts, a completely new user who also has a balance greater than 1,000 UAH and commits the changes. If Transaction A repeats its query, it will now see 6 records. This 6th record is the phantom. It appeared out of nowhere during the transaction's execution. The main difference from a non-repeatable read lies in the nature of the changes. There, existing rows were modified, whereas here, new ones are added, changing the result of a query on a whole set of data. The last of the main problems we will consider separately is the lost update. This is a classic write-write conflict scenario. Imagine you and your colleague open the same file for editing at the same time. You both see the same initial text. You make your changes and save the file. A second later, your colleague, who hasn't seen your changes, saves their version of the file over yours. The same thing happens in databases. Two transactions read an initial value, e.g., quantity of goods in stock equals 10. The first one sells one item and writes 9. The second one also sells one item, but it calculated 9 from the initial 10 and also writes 9. As a result, instead of 8 items remaining in stock, since 2 were sold, there are 9. The update from the first transaction was simply overwritten by the second. This is a critical error for any accounting system. To solve the described problems, the SQL standard defines 4 isolation levels. The choice of level is always a trade-off between data reliability and system performance. Read uncommitted, chaos mode. Transactions see everything, even uncommitted changes from others. It works very fast because there are almost no checks, but the data can be incorrect. Read committed, the golden mean. You only see what has been definitely committed. This is the default mode for giants like PostgreSQL and Oracle. It protects against dirty reads. Repeatable read, increased strictness. If you read data once, the system guarantees that it will not change until the end of your transaction, no matter what other users do. Serializable, paranoid mode. The system behaves as if users are working one after another, in sequence. This completely eliminates any anomalies, but significantly slows down performance due to constant resource locking. This concludes the topic of transactions. We have examined the transaction mechanism, which is essential for any reliable system, discussed the ACID properties, and learned how to prevent conflicts when many users are working simultaneously.